All right, this is our last lesson for chapter 12, and this is going to talk about reaction mechanisms. And that's just a fancy way to say the series of steps that happen in a reaction. So we've talked about the fact that most reactions we write as one step, but it's actually a series of steps that we combine into the final reaction. And the reaction mechanism is not known by scientists. We can't figure out some of them, and so we have to infer what they possibly could be. And so scientists will come up with possibilities, and those possibilities have to satisfy two requirements. First of all, the sum of the elementary steps, that's the small steps that equal the overall, they have to add up to give the overall balanced equation. So if you remember Hess's law, where you can cancel things that are on either side of the arrow, they have to add up to give you the final overall reaction. And the second requirement is that the mechanism must agree with the experimentally determined rate law. And what that means is once they come up with the rate law, it's based on the slowest step that you have. Kind of like you're only as strong as your weakest link. The reaction can only proceed as fast as the slowest step. That's the one that limits how fast it can go. And so it has to match the slow step has to match the reaction mechanism. And I'll show you what I mean by that in an example in just a minute. There's a few more terms you need to know. There's something called an intermediate, which is something that's not a reactant or a product, but it's something that's formed in the reaction and then it's consumed. So in this example that I have up here, an intermediate would be CD, because notice that CD was formed in the first reaction and then it was consumed in the second reaction. Elementary steps is the term for the individual steps that add up to be the whole. And their rate laws can actually be written from the reaction. You don't have to do experimental data on those. All you have to do is use the coefficients as the exponents. However, people love to do that all the time. And make this note right here, you can only do that if it's an elementary step. So if it's an overall reaction, then you have to do experiments to get that data in order to get those exponents. Molecularity just means how many molecules you have. So uni is 1, bi is 2, and ter is 3. So there's some examples you can see there, and you can see what the rate laws would be. Note that these are elementary steps, so you can just use the coefficients as the exponents. Like I said, the rate determining step is the slowest step in the reaction. And here's an example in letter F. So you have this overall reaction. They determined that this is the rate law right here. And they came up with these two elementary steps. So if you're trying to prove whether or not these elementary steps are plausible means they could actually be elementary steps, the first thing you want to do is see if they add up to give the total. So notice that I crossed off NO3 because it's on the left here and it's on the right here. I crossed off one of the NO2s because it's here and here. And so what we're left with is one NO2 on the left, which is like this one CO on the left, one NO on the right, and one CO2 on the right. And so when you add up those two equations, you're going to get that overall reaction. So it does fit the first requirement, is that they must add up to give the overall reaction. The second requirement is if it fits the rate law. So if the rate determining step is step 1, then the overall then the rate law is going to be rate equals K. Let me this right here. And if it's step 2, then it's going to be this. And since they said it was this one, then that agrees with what they told us. So you just have to look at the steps and see which one is the slow step and see if it matches the experimental rate law. Note those stars. We don't know for sure what the elementary steps are. We just use chemistry to make inferences, and again, you have to make sure that they match. This talks about the collision model, which we actually mentioned at the beginning of this chapter because I think it's really important for kinetics. Anytime you're explaining why something happens faster or slower in a reaction, you want to be able to talk about these two things. That if you can increase the chances that one or both of those would happen, then you're going to increase the rate of the reaction. And they also go into detail about the energy diagram that we've talked about several times, but note that I made a note in my notes that students tend to forget this, so to go over it well. So let's just review. This is showing you the energy of a reaction. So we're starting with reactants over here. Notice that they have a pretty high energy, high on the y-axis. And then we're ending with products down here. And notice that they have a lower energy. And because of that, that means that they lost energy. The reactants lost energy to the environment, which is why we call this exothermic, because it released energy. The activation energy is the energy the reactants have to gain to get over the hill. So you're not going to go all the way down to the x-axis. You just start at the reactants and go to the top of the hill. So that's the activation energy. The enthalpy is the difference between the reactants and the products. So this right here is the enthalpy. And then the activated complex is the thing that exists at the top of the hill right here. So it's kind of an in-between state. It's not really the reactants, it's not really the products, it's just kind of in between, and it's very high energy. And if they're talking about the energy of the activated complex, that is this entire amount right here. And I always tell my first year students to watch for that X at the end of complex, and that means you will go all the way down to the X-axis. Activation energy does not have an X in it, so don't go all the way down to the X-axis there. And then if it was endothermic, let me just show you that. So that would be, it would look like this, where you have low reactants and then they gain energy and become higher on the product side. So make sure you can label all of that graph. We've talked about catalysts before. Catalysts are something that speed up the reaction by lowering the activation energy. So if we go back to that collision model, the particles have to have enough energy to get over the hill in order to react. So if you lower the hill, then more particles have enough energy to get over that hill, which means the reaction will go faster. These are a few things that you just want to be familiar with. Catalysts lower the activation energy, but they don't change the delta H. So they don't change the difference between the reactants and the products. They provide an alternate reaction pathways, and like I just said, they have a higher percentage of effective collisions. And the very last thing for this chapter are intermediates versus catalysts. A lot of students mix these two up. So intermediates are things that are formed and then consumed. So notice that C was formed in step 1 and then consumed in step 2, and so it ends up canceling out, but it starts as a product and ends as a reactant. That's an intermediate. A catalyst is something that you add it to the reaction, and they're not used up though because they're produced again. So letter B is a catalyst because you added it to the reaction, but then it got used up like later down here. Or I'm sorry, it got used up, but then it was produced again. So B is still going to be crossed off, but notice that it started as a reactant and ended as a product. So again, this one starts as a product, ends as a reactant, starts as a reactant, ends as a product. And it'll still cancel out. So the catalyst is not going to be written in the final reaction. And that's it for chapter 12.